Okay, we left off here with number 8, and we have to sketch a graph of a function with a set of properties. These questions, which by the way, if you take calculus here at OU, you'll certainly come across these quite a bit. They can be nice in that there's many answers. They can be difficult in that sometimes it's hard to know where to start. So sometimes you just have to jump in. In this case, we want a real root at x equals negative 3 halves. So we can go ahead and plot that. That'll be a definite concrete point that we have to do. And then multiplicity 1. All that tells us is we're either going to go through from bottom to top or from top to bottom, but we're not going to bounce off the axis. So we can't really know if we're going up through or down through until we move on. So we also want to be increasing on negative 4, negative 1, not necessarily including that negative 1, and negative 1 to 2, and decreasing on 2, 4. So your first question might be, why don't we just increase from negative 4 to 2? So start at negative 4, increase all the way to up here, 2. Well, we also need a local minimum at x equals negative 1. So we could have potentially gone like start going up, going up, going up, and then dip down for that local minimum, but then we'd run into problems because we need to be increasing basically from negative 4 all the way to 2. Our graph should be going up, and that means the y value should be increasing as we're going from left to right. Now, we get into an interesting situation here. Negative 1, at that exact point, we're not required to increase. So we have this option to jump. So notice that we're increasing, increasing, increasing all the way to negative 1. And then right here, we drop down, and then we're increasing, increasing, increasing all the way to negative 2. So we're increasing all the way between negative 4 and negative 1, and between negative 1 and 2, just in an odd way there. And we need a local minimum at x equals negative 1, which is why I dropped that point down low. Notice that this point is defined, the domain is defined on both sides of it, even though we have that jump discontinuity. And it is less than the points immediately to the left. The y value here is less than, and the y value is less than those points immediately to the right. So we have an open interval in the domain where this is the lowest point. So it's a local min. And then the final thing is we just need to be decreasing from 2 to 4, but we do have to be careful not to touch the x-axis. Why? Because that first statement said the only real root is at x equals negative 3 halves right there. So we do have to make sure not to create any more roots or any more zeros. Okay, putting this in standard form, we're essentially completing the square. So first I'm dividing everything by 2. Dividing the first 2 by 2. I'm peeling off that minus 3 and putting it outside the area that I'm working with here for a second. And then I divide these other 2 by negative 2. I pull a negative 2 out in front, and you can't really see that negative there, but it is. And hopefully on your PDF that you downloaded, you could see it. Once we pull a negative 2 out, we're going to leave a blank spot here because we want to fill in something that's going to get squared. And we notice that half of negative 2 is negative 1, which is what we're eventually going to put in there. But when we square negative 1, we're going to get plus 1. But if we add 1, we also have to subtract it. So that's why we're doing all that. And right here, this x minus 1 is now squared. We have the x squared, the minus 2x, and the plus 1. We have everything we need to have x minus 1 squared. That negative 1 gets pulled outside, so why did I change it to positive 2? Well, because it's getting multiplied by that -2. Everything inside here is getting multiplied by that -2. So when I said that I added 1 and subtracted 1, I really lied. I really subtracted 2 and added 2, if you think in terms of what's really happening to the right side of the equation. So that -1 times -2 becomes a +2. Combine those to get -1, and now we're in standard form. The other three are pretty straightforward. The vertex is going to be what we're subtracting from the x, which is +1, and what is getting added on to the end, which is -1. That's our vertex once it's in standard form, which it is. And the axis of symmetry, then, you can see on a vertical parabola is just going to go straight through that vertex, and it's going to be a vertical line, so we have x equals 1, which is the x-coordinate of the vertex. Where are we increasing and decreasing? And when we ask increasing and decreasing, we mean as we go from left to right, what's happening to the y values? So as we go from left to right, the y values are increasing up to and including the vertex. So that puts us from -infinity to 1, including 1. And from 1 on, we're decreasing. Our y values are decreasing. Notice that that 1 got included in both intervals. That's just based on the definition of increasing and decreasing your book gave. So it is possible to have that borderline point on a continuous function be included as increasing and decreasing. And is your vertex a max or min? Well, you might know it's a max because this parabola has a -a value, so it opens down. So because it opens down, the vertex is a max. We can also look at it more analytically. If the function is increasing on this interval, that means, by definition, that means that f of 1 is greater than or equal to f of x for any other x's in this interval. Similarly, if it's decreasing on this one, we know that f of 1 is greater than everything in this, so f of 1 is greater than f of x for the entire function, meaning that it is an absolute max. Finding the real zeros, several different ways you could go about this. I looked at the rational root theorem, so we took all the integer factors of 2 over all the integer factors of our coefficient of our leading term, which is just 1. So that really just gives us plus or minus 2, plus or minus 1. I just tried +1 because it's the easiest. I plugged it into the original function and got 0, which tells me that x equals 1 is a root. If I would have plugged it in and got something other than 0, we can determine that it's not a root. Once I know that +1 is a root, I use synthetic division here, and I'm writing out the coefficients of the function. Notice that the x² term is not existent, so that's why I have a 0 right here to represent it. And once we go through that, we should end up with a 0 to tell us that basically what I'm trying to do is I'm trying to factor this real root of 1 out of p of x to see what I'm left over with. So when I factor that out, I get x minus 1, which again is the same as saying there is a 0 at 1. And I also have this x² plus x minus 2, which breaks down just by standard factoring into x plus 2, x minus 1. So we have a 0 at x equals 1 with a multiplicity of 2, because there's 2 of them, and at -2 with a multiplicity of 1. Okay, 2 more problems here. So number 11 is a fairly difficult one. We have x² minus 3. What I would do is just draw y equals x², the standard parabola, and I know that that minus 3 at the end is going to shift it down 3. Another way you can do it is just put in several x values, find the y values, and then plot these 5 points, which is right here, 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 and here. And then I did the same for g of x, which is an absolute value function. you may be able to realize that that negative is flipping it over. This 3 is raising it up by 3. If you don't, again, just plot out a table of values. I'm kind of arbitrarily choosing some positives and negatives that are easy to calculate here for my x's. And then once I plot them, I can see that I have this upside down V shape. And the final question asks, for what values of x is f of x less than or equal to g of x? Well, f of x is this parabola. G of x is this upside down V. So notice that everywhere between here and here, between x equals -2 and +2, I'm strictly less than, and on those 2 points, the two functions are equal. So I'm going to say that the answer is -2 less than or equal to x less than or equal to 2. If the question had asked me to do interval form, I could have done a square bracket, -2, comma, +2, square bracket. And finally, we have a polynomial here. It's written in factored out form. What is the degree? Well, I just need to know what the power of x is. So I know there's going to be an x here, an x here, an x here, and an x here, all getting multiplied. To be safe, I maybe should check out that nothing's going to cancel out, but it's pretty clear here that there's only one x in each of these. So since I have 4 x's, the degree is 4. In other words, my highest term is an x to the 4th term. And we actually see what that term is in part B. So to find the leading term, we need to multiply all of the x's. So we have a -x, +4x, x, +2x. Multiply those 4 together, we get -8x to the 4th. And really, I'm just multiplying the coefficients and then multiplying the 4 x's. In the constant term, I'm doing the opposite. I'm multiplying everything that does not have an x. So a 3, a 2, a 1, and here notice, this term right here does not have this factor here does not have a constant term. So in a sense, that's 0. So there will be no constant term. If we multiplied that out, notice another way to think of it is this 2x is going to get multiplied by anything that comes out of these first 3, which means it's not possible for there to be something left over, a constant term left over without an x on it. So the constant term is just 0. And the end behavior really all depends on that leading term. So we have that -8x to the 4th. As x gets smaller and smaller and smaller, that small number is going to get multiplied to the 4th, which will make it a positive, but then it gets multiplied by that -8, and so we're going to go out to -infinity. And by the way, when I say x gets smaller and smaller, it's a larger number, but it's just a negative. So that x to the 4th is actually going to be a very high number. It's not, I should clarify, it's not going down to 0. So think of -1,000,000. -1,000,000 to the 4th power is going to be 1 followed by 24 zeros, huge number, and it's going to be positive. Then it gets multiplied by that -8. As x goes to positive infinity, in other words, x goes to 1,000,000, then 10,000,000, then 100,000,000, and on and on and on, multiplied to the 4th power, or raised to the 4th power, it's going to mushroom that even more, but it'll be positive, and then it gets multiplied by that -8 finally to make it a negative. So we can get as low of a y value we want in either direction. It's going to go down on the ends in both directions. Okay, that is it. Again, please let me know if you have any other questions. Thanks.